Hi, welcome to Lecture 10 of ECE 141, and this is about an introduction to information theory. This marks the start of looking at the looking at the communication system in an abstract level instead of something physical, like our previous 9 lectures, where we looked at the communication system as a block diagram. Now, we're going to formalize the mathematics behind transfer of data between one point to another in terms of the bit level view of our communication system. Since we're talking about digital communication system, we're going to talk about bits. And in terms of the bits that interact from one device to another, or the bits that we transfer from one device to another, how do we model or how do we look at it in the higher abstraction level or the bit level? And that is how information theory was actually developed. Okay, but first, what is information? We tried to define it before in the perspective of a communication system. It's actually difficult to define. We can only represent it as symbols from a constellation or a symbol space, or it could be a signal, and so on and so forth. Right. Uh, Consider your daily lives. Okay. Recall moments from your daily lives. You always obtain information, and you obtain it by learning something new. Consider the following sentences. Excuse me. These sentences convey information. For example, the weather will be good tomorrow. How'd you know? It was the forecast from the news, from a reputable news source. Okay. Oh wow, I learned something new. It's new information. So now I'm more certain that the weather will be good tomorrow because I learned that from a reputable news source, from a reputable weather forecaster, that the weather will be good tomorrow. So basically, your uncertainty of the weather tomorrow, your uncertainty of the weather tomorrow has been reduced. Okay, and so on and so forth. I will get a passing grade in ECE 141 this semester. How'd you know? Well, I passed all the exercises, I do all the laboratories. When I get my scores, it's always has a passing grade. So I'm more certain now that I will pass ECE 141 this semester. Right. Basically, the uncertainty of you passing or not passing ECE 141 has been lessened because of the new information that you have gained. In other words, one gets some information when learning about something that he or she is uncertain before. So, the definition of information formally, according to Shannon, which revolutionized information theory, information is the resolution of uncertainty. So, among these four, which statements do you think contains the most information? I'll leave that to you. Okay? And if you have some thoughts, maybe leave a comment in the comment section below. So let's proceed. So let's look at sources of information. Uh, in our digital communication systems, the sources of information are discrete sources. So let us uh, view all information sources as discrete. It could transmit symbols, or it could transmit bits, whatever. Basically, it has a discrete number of possible outputs. All right. So the data output y has a discrete uh, value, and it's a random variable. So it comes from a set with finite cardinality, as you can see here. Y could be y1 to yn. Each element of the set has a probability that is going out. So basically, if you try to sample it, there's a probability that it's y1, there's a probability that it's y2, and so on and so forth. So an example of a discrete data source is your English alphabet. If you have a data source, maybe a letter, you wouldn't know what's coming out next. But you know that it is either A, B, C, D to Z. Another example is Morse code. Another example is Braille code, and so on and so forth. Basically, discrete sources, you have already interacted with them before. So now, mutual information. Let's say you transmit this data through a channel. So the data source has a variable x transmitted over a channel, and you have another random variable y. So now these two can be treated as different data sources. So this channel y sends a data, or this channel y outputs a data, okay? And suppose we can only sample y, of course. That's our communication system. We sample y. So by observing y, can we get information about x, which is the actual message transceived? Sorry, transmitted. Okay. So suppose we are sampling y. We want to know what was transmitted, which it was x, but we can only sample y. So recall that this is actually an a posteriori problem. We want to know what is x given y. Okay? So x would be from a set x bar, y would be from a set y bar, and both of these sets are a finite cardinality. So basically, they're only contained between some number of elements or symbols. The mutual information can now be defined as this. So we define the mutual information between y and x to be equal to this. Okay? So how do we interpret this definition? This is the amount of information that y tells us about x. Basically, if we observe y, we get some certainty on what x is. For example, the weather tomorrow will be good. Okay? How do you know? That's what the forecaster told us. Oh, so now you have some certainty of what the weather is tomorrow. So that's kind of what it means to be, or what it means to have mutual information between two data sources. Okay, so this is just the mutual information between the two events, x and y. The total mutual information between the random variable x and y, so this is different. As you can see, small x and small y, these are just the mutual information between the two events. Between the random variables, you need to sum everything. So it's a weighted sum of all the mutual informations. Okay. The units of mutual information will depend on the base of the logarithm. Base E has a unit of nats, while base 2 has a unit of bits. So in the future, we'll be focusing on the bits part of mutual information, but let's generalize it first. Right, so it depends on the base of the logarithm. So just some properties of mutual information. It is symmetric. Basically, if you swap the variables, it should be equal. And this is the proof. I won't bother you with the proof. Okay. So basically, mutual information is if we flip it, I of yx, that should be equal to I of xy. Right? And this is the proof. So I won't bother you with much detail. Right? Basically, you'll just use base rule. If you use base rule, and you'll still get the same answer. Next, mutual information is non-negative. Right? And this is the proof. Right? So it's non-negative. Basically, it just tells us that the probability of x given y is greater than the probability of x, which makes this logarithm positive. Right? And that's a fundamental property of your probability distributions. Right? So that's what makes mutual information non-negative. So let's look at independent events. We're calling probability theory that if two events are independent, then their joint probability will just be equal to the product of their probabilities. Since these events are independent, their a posteriori probability, or let's say the probability of x given y, which is equal to this, will now be equal to p of x. Okay, so if you substitute this, we get p of x. That means the mutual information given by these independent events becomes zero. To interpret that, what does that mean? It means that by observing y, we do not have any information on x. So if we observe y, then we don't know anything about x. We're still uncertain, the same as before. So consider the scenario when you're attending a lecture and you still don't understand anything. Maybe it's because that lecture is independent of what you are studying. That's how you can interpret it. By attending this lecture, you did not understand anything, therefore you did not gain any new information. Right? So that's an example of an independent event. What if we have dependent events? So let's say we have an extreme case then. Say y uniquely determines the value of x. So by observing y, we know exactly what x is. That means for any element of the set x given any element on the set y, basically the a posteriori probability becomes equal to 1 for any given x and any given y. So your mutual information will be simplified into this expression right here. And we call this the entropy of the source I of xy. So entropy is also called self-information. Okay? So your independent versus dependent events could be visualized as something like this. If your x is independent of y, then your channel is basically disconnected. If your x is completely dependent on y, maybe just short the channel. Okay, that's how we model it. So now let's look at the concept of entropy. It's the information of mutual information of a variable with itself, which is equal to this. So the entropy is of a random variable is a measure of uncertainty or ambiguity. The higher the entropy of the data source, the more uncertain you are of what is coming out. If we observe x, uncertainty about it is removed. By consequence, h of x can be thought of as the measure of information acquired by observing x, because it's derived from the mutual information, as you can see here. Okay? But the self-entropy or the self-information of your data source defines how uncertain you are when you are trying to guess what value is going to come out of that data source. That's the interpretation of entropy. Just some properties of entropy. Since it is derived from h of x, from I of x, right? Rather, h of x is non-negative, it's always positive, and its upper bound is this value right here. Basically, the upper bound is the logarithm of the cardinality of its set. More, excuse me, the more uh, the more elements your set is, the higher the maximum entropy of your source is. The mutual information of your data source with itself is its entropy. That's how we defined it earlier. So entropy is also called self-information. So if we have mutual information between x and y, its maximum value is the minimum between the entropy of x and the entropy of y. So if y is a function of x, then h of y is less than or equal to h of x. This tells us that if we have y here, which is dependent on x, or as a function of x, then the entropy of y, which is when we observe it, we're already more certain of the value of y compared to x. That's how we interpret this equation right here, or this property of entropy. So let's look at how entropy is bounded. We already know it's non-zero because it is derived from or defined from mutual information. But how did we arrive at this maximum value right here? Okay, so this is the entropy will be zero if your source only outputs one data all of the time. This occurs when some x, which is an element of your finite set from your data source, the probability of that is equal to 1, all the others 0, your entropy will become 0. Okay? You get that from the formula. Then this source is actually always generating the same symbol every time. You don't get any information from it at all. So it kind of like someone who just says the same thing over and over again. Do you learn something new from that someone? No, right? So that's how you interpret that. But where did this upper bound come from? We are most uncertain when h of x is equal to the logarithm of c of x. And this occurs when your probability of your output is equiprobable. Basically, all your data is equiprobable. So you get the most the most uncertainty when the data set is equiprobable. Kind of like when you're rolling a dice. If you're rolling a die, you don't know what will come out, right? And if this die is not biased, okay, basically all the faces are equiprobable in occurring, then you're not certain what will come out. If it's a loaded die, then you're more certain compared to when it's a fair die. Because if it's a loaded die, then it rolls more towards some value compared to when it's a fair die when you don't really know what will come out. Okay? And that is a property of entropy. So you're most uncertain when you don't know what's going to come out. And that is when your data set is equiprobable or uniformly distributed. For example, let's say you have a binary source where the probability of having a 1 is p, which means the probability of the other side 0 is 1 minus p. The entropy is equal to this. If you try to plot that, it will be maximum at equiprobable symbols. Okay. So another example, maybe let's make it continuous. For a continuous source, instead of a summation, we'll use an integration. Okay. We'll use an integration. So let's say your probability is a Gaussian random variable. Okay. So for a Gaussian random variable, you have this expression. If you take, if you get, try to get the entropy of that, the entropy is equal to this. And actually, it can be shown that for a given variance, the Gaussian random variable exhibits the highest entropy, which tells us something. Right? So if you have some if you have some output, let's say noise, from a communication system. Let me try to draw that. Let's say you have some noise, you're trying to guess the pattern of the noise from a communication system. So let's say the output of that is n. There you go. If you're trying to guess the value of n, or trying to guess its pattern at the very least, for a given noise power, which is dependent on variance, you're most uncertain if it is a Gaussian random variable. So you don't really know, you can't predict it. As compared to if you have a uniformly distributed noise or a discrete noise, so on and so forth. Basically, you're most uncertain if it's a Gaussian random variable. Right. Now, let's define what we call the joint entropy. So the joint entropy for two random variables x and y, we define a joint entropy to be equal to this. Basically, They will just be based on the joint probability of the two random variables. And this is different from the information, from the mutual information case. So this is the case when your random variables are separate from each other, like this, right? And you want to get the total entropy of the system by trying to guess the value of x and y simultaneously. That is the definition of joint entropy. And if you have multiple random variables, it will just be based on their joint probability. Conditional entropy is equal to this. So if the random variable x is given to be some x, small x, then the entropy of y given x is equal to x is basically equal to this. So you get the probability of all the y, all the possible output y given your single x times the logarithm of the probability. Okay. So if we average this term for all possible values of x, we get the conditional entropy of y given your random variable x. Okay. And the properties between them is that your joint probability is equal to the entropy, sorry, the joint entropy is equal to the entropy of one plus the conditional entropy from the other one. And you can actually reverse the variables in this case. The conditional entropy is always positive. It's a property of entropy. And it's bounded by the entropy of the random variable. So this is the case when your y does not have anything to do with x, basically. The maximum value of the sum of the entropies of h of x and h of y is basically the sum of their entropies is the maximum value of their joint entropy. And this occurs when x and y are independent of each other. Okay. And finally, the mutual information about both x and y, if we try to observe x, or if we try to observe x, we get less, or we get less uncertainty, or we become more certain with the value of y. We can get the mutual information based on their entropies. Okay. Now, if h of x, y, or x and y are independent of each other, then this h of x, y will be equal to this, and the mutual information about both x and y is 0. So you don't get any information by observing y. You don't get any information on x by observing y. So how do we interpret the conditional entropy then? So recall that observing y will give an information on x. And h of x given y is the uncertainty on x when y is observed. Basically, if we observe y, we get a feel of x, or we get an observation that will define the value of x. What is left, okay, if what is left will be h of x given y. And the goal is we want this to become 0 if we observe y. We want to get the entropy, or the uncertainty on x, to be 0 when we observe y. That's the goal of your communication system. If y uniquely determines x, then your h of x given y equals 0. Okay. So now let's look at the relationship of conditional entropy and mutual information. So using property 1 and property 4. So property 1, the mutual information is equal to this. Property 4, your conditional entropy is bounded by 0 and the self entropy of x. If y uniquely determines x, basically this I of xy should be equal to 0. Okay? Or yeah, if y uniquely determines x, rather, I of xy becomes h of x. Sorry. Okay. So that's what happens when y uniquely determines x, which means complete information about x can be observed from y, and that will make h of x given y be equal to 0. If x is independent of y, then we don't get any information on x if we observe y. And that would mean h of x given y will be equal to h. Still, it's still h of x basically. So that's how they are related from each other. Okay. So now, how does the discrete source transmit or convey information to its destination? So as we know, information is abstract, but entropy defines a measure of information. But how do we interpret it as a system? We've done this before actually. We have a discrete source, we represent it as symbols. And that process is actually called source coding. It's a method of representing information. Now the goal is we have symbols. We want to represent them as bits because we're operating in a computer, in a digital communication system. So the goal of source coding theory is to represent the information from a discrete source without errors. So emphasis on without errors. Okay? For example, if we want to represent the numbers 0 to 3, then we need 2 bits. And we have 0, 0, 0, 1, 1, 0, and 1, 1 right here. Some more examples of source coding. Maybe the letter A can be represented in different forms. In spoken language, it's A. In written, it could be capitalized or lowercase. Sign language, we have this notation or this notion rather for sign language. Morse code, it's a dot and dash. Braille code, one big dot and five smaller dots. ASCII code, it's 065. And a binary code from your ASCII table is 01000001. More about source coding in the next lecture. Okay. So if you have any questions or do you need any, if you need any clarifications in this lecture, I'd be happy to discuss with you in the comment section below. Thank you for your time. See you next meeting.